So now let's kind of step it up a little bit here and go over a little bit more in-depth example. The last one I just gave you the concentrations. But in most cases, when you mix two solutions together, the concentration is going to change a little bit. I'll show you this example here. So the next example is that if we take 100.0 milliliters of 0.040 molar MgNO3 solution and mix it with 150.0 milliliters of 0.75 molar Na2SO3, will a MgSO3 precipitate form? The KSP value listed for magnesium sulfite is 3.2 times 10 to the minus 3. And as a note here, we're going to assume volumes are additive. So what this means is I have a beaker over here, and the first thing I'm going to do is I'm going to add 100 milliliters of our, or 100.0 milliliters of our MgNO3 twice solution. So over here I have magnesium 2+ cations, and I have nitrate anions. I have 100 milliliters of that. Then I'm going to add 150 milliliters of our sodium sulfite. So that means now I also have sodium plus ions in solution, and I have SO3 2- ions also in solution. We now have a total volume of 250.0 milliliters. So when we add these solutions together and we combine them, our concentration is going to change. Because remember, concentration is moles per liter. If I have a certain concentration down here of our magnesium 2+, when I add another solution to that, the moles of the magnesium right here are not changing, but the volume is. So the concentration is going to go down. So typically when we dump these two things together, we have to take into account the total volume of our overall solution. So if we set this up, if we think about what our solubility equilibrium expression is going to be, we have MgSO3 as a solid, and it's going to be in equilibrium with magnesium 2+ ions in solution plus SO3 2- ions in solution. Our Q here is going to equal magnesium 2+ times the concentration of SO3 2-. So now what we have to do is we have to calculate the concentrations of each of these species in solution. Our concentration of our magnesium 2+ is going to equal the moles of magnesium 2+, which we can calculate by taking 0.040 moles of Mg2+ per liter times 100 milliliters, which would be 0.1000 liters. And this is going to be divided by the total volume, which in this case is 250 milliliters, or 0.2500 liters. Okay? The liter units cancel up here in the numerator, so we have moles of Mg2+ divided by liters of solution, and this is going to give us a concentration of Mg2+ of 0.016 molar. Now we need to go ahead and do the same exact thing for the concentration of the SO3 2-, and this is going to be 0.75 moles of SO3 2 minus per liter times 0.1500 liters divided by our total volume, which is again 250 milliliters or 0.2500 liters. This gives us a concentration of 0.45 molar. So our Q expression, plugging it back into our formula, is going to be 0.016 times 0.45. This gives us a value of Q that's going to be 7.2 times 10 to the minus 3. In our particular case, for this particular problem, our Q is going to be greater than the KSP, so we can make the conclusion that therefore Mg SO3 will precipitate. Okay? Does anybody have any questions of kind of what we did there? The key thing in these particular problems is we need to know the concentrations of all the ions of interest. The ions of interest in this case are the magnesium 2 plus and the SO3 2 minus. Okay? We figure out those concentrations from adding the solutions together and taking the total volume. Okay? Then we compare Q and the K and figure out if a precipitate would form. Yeah? Question in the back there? So the question was, what happens if you're given a question where you're looking at molar solubility and you need to figure out the KSP? Molar solubility, typically we set up an ice table and we say that X moles of a particular solid will dissolve. Okay? In this case, since the cation to anion ratio is 1 to 1, it would be X times X, and the KSP is going to be X squared. Okay? But in some instances, for example, the calcium iodate from lab, you have calcium 2 plus, which would be X, and then the iodate would be 2X. Okay? So the molar solubility, we're looking at just the value for X. Okay? But when we go to the KSP or you do any other calculations like this, you must be sure you keep track of the cation to anion ratio. Okay? Does that make sense? Okay, good.